All right. So this is our second lecture on nonlinear solvers. We barely touched the surface last time, went over a bunch of definitions and just that. But today we're going to start digging deeper into nonlinear solvers, and we're going to learn at least one method. Hopefully we can get to two methods. And last time, if you recall, we left off at this thing called the residual function. We were talking about finding the root of a function, f of x, like could be cosine x or log cosine x equal 10. And we said that the root of this function, which means that it's the point that where the curve f of x, the red curve, intersects the line y equal 10, is the same as the root of the function f of x minus 10. So if you do f of x, move everything to the left-hand side, put that equal to 0, and define all of that as a new function, call that the residual function, then the root of that residual function is the same as the root of the original equation you started with. Now, we call that approach the residual function, and it's a way to standardize our discussions of nonlinear equations or equations in general. So from now on, we will always assume that we are dealing with residual functions. So I give you an equation, cosine x squared equal 10 log x plus 15. Then you move everything to the left-hand side and you call that your residual function. When I say we're finding the root for that equation, it's equivalent to finding the root of the residual function equal to 0. Okay, so because we want to bring everything so that curve, the residual curve, intersects with the line y equals 0. It just simplifies our discussion. All right, so I have to switch back to my slides here. Okay, so now your question to you is, go ahead and find the residual function for log x plus cosine x squared equals 3. So that's an equation, and I'm asking you to find the root for that equation. First thing we want to do is write this in residual form. So go ahead and write it in residual form. I will stay on YouTube, and then I'll just show you the answer over here. We don't need to discuss this on Zoom. Just write it in residual form, write the residual function r of x equal what? And then our goal will be to find the root of r of x equals 0, okay? So I hope you got that, figured out. It's just simply a matter of moving everything to the left-hand side. So you define r of x equal log x plus cosine x squared minus 3. And when you set that equal to 0, then that's the equivalent of saying I want to find the root, the value of x, such that this curve, log x plus cosine x squared minus 3, intersects the y-axis equals 0. And the root of this equation is equal to the root of the original equation we started with. Okay, so now on to our second activity. Remember the problem we started out with. It was the problem of the parachutist, and we were looking at finding the drag given a certain parachutist mass that will reach a certain velocity as they're falling down the atmosphere. Find the drag coefficient such that they reach a certain velocity after 10 seconds. The specific example we did was find the drag coefficient for a parachutist of with a mass of 70 kilograms for them to reach 40 meters per second after 10 seconds of falling, okay? And then you all recognize that this was a nonlinear equation, all right? And so the first step now in our attempt to solve this problem numerically is to write this in residual form. So go ahead and spend a minute, write this in residual form, okay? I changed the nomenclature here a little bit. It's no longer x. So think about what you're looking for, and you define your residual function as a function of whatever unknowns you're dealing with. Okay, I'll see you in a second. All right, I am back on Zoom, and you should be able to see the slide of the equation for which we're trying to find the root C. You should see it there on YouTube. So in this particular case, we're going to set a value for U. On the left-hand side, we're going to set a value for M. We know what G is, that's gravity, and we're going to set a value for T. The only unknown would be C, the drag coefficient. And we're going to extract C given all of those other numbers, okay? All of those other variables have mixed, okay? But to do that, we need to first write this in residual form. Remember, U of T is a value, okay? It's not just like a function where we said f of x equal log x and say that is equal to 0. No, over here what you've got is mg over c into 1 minus exponential, etc., equal u. And those are all values, okay? Let's see, has anyone made any progress? Still scratching your heads?
I could try.
All right, go ahead.
What I was thinking is that so you have U of T equals all of that.
Mm-hmm.
So you take all that over to the other side.
Yep.
So you have U of T minus mg over c equals 0.
Exactly.
And that would be your R of T.
Yep, as simple as that. So that entire thing is your R, is your residual function. You know, you could call it R of T, or you could call it R of C, or R of everything, whatever, right? That's very specific, but yeah, this is it. So the trick here is not to think of U of T as we thought about previously f of x. No, U of T is a specific value now that is given to you equal to something, and once you substitute all the known values, you still have one unknown, that's C, the drag coefficient, and you want to solve that entire equation for that C. All right, I'll show you on YouTube how it's done. All right, just like Matthew told us, you simply, in this case, all you have to do is put everything on the left-hand side or move everything to the right-hand side, whichever. So in this case, I moved U of T to the right-hand side. Doesn't matter, you're still gonna get the same root. And I defined my residual function as R, call it R of T, but really in this specific case, because I'm searching for the a drag coefficient, I want to call it R of C, okay? But that doesn't matter still, as long as you know what your intent is. Now, this would be our residual function. Think of U of T as a specific value that you are reaching, that's given to you. M and G are known, and T is known, and all you're trying to find is C. So that's the equation that we need to solve. That's our residual function, and that's what we're going to be dealing with. All right, so now we can start our discussion about nonlinear solvers. We haven't talked about nonlinear solvers yet. All we've defined are residual functions and what we mean by a nonlinear equation, et cetera, et cetera. All right. For nonlinear solvers, for the vast majority of cases, as you've probably have realized now, nonlinear equations are difficult to solve by hand or impossible. Only in a few cases you could solve those by hand. So you need a numerical mechanism to get the solution. A nonlinear equation might have no solutions at all. So in other words, your residual function does not intersect the x-axis or the y equals 0 axis, or it might have many solutions. Think of a sine function or a cosine function that intersects the x-axis many, many, many times. So knowing what interval you're dealing with will help you home in on the root that you're interested in, okay? We will also see how the initial guess for your nonlinear solver is going to tell you to which of the roots you're going to converge. Okay, we cannot claim that a particular nonlinear solver is going to find all the roots for you. You got to give it the initial guess and kind of hint it in what direction it needs to converge towards. The solution methods are all iterative in nature and require an initial guess. So we're going to start with an initial guess and start refining, develop a recipe and start refining that initial guess, just like we did with linear, iterative solvers. You're not guaranteed to find the solution. We'll show a few examples of that. Excuse me. And the initial guess is critical in finding in being able to find the root. Okay. We discussed what the residual form is. There are two general approaches for nonlinear solvers. We categorize those as closed domain and open domain methods. The closed domain methods are the simplest and most intuitive, and we're going to start with those. They're not usually always practical for very complex problems, but they are really great for simple calculations, and they can be used in big nonlinear solvers in practice to help the general nonlinear solver converge. And the idea with closed domain methods is that you say, look, I know that there's a root somewhere over there, somewhere between some lower value and upper value. And I'm going to use that bracket and start refining it to home in on the root. And you could do this by plotting the residual function, for example, and say, look, visually, I see there's a root over there. It's around 1.3, let's say. All right. So, but I don't know exactly where. I need to get to that root very, very in a good precision. So you pick 2 points around that root and you start homing in. Now you could say, oh, I can just evaluate the function randomly between around 1 point around where I expect the root to be until I know that the residual function is very close to 0. That's certainly a legitimate way of doing it, but there's no reason to the madness there. You're just evaluating randomly. You need a mechanism to help you figure out where to evaluate next. And those are the closed domain methods. We're going to develop recipes for those. We'll learn about the bisection and the method of false position, or regula-falsi as it's called. And then there are open domain methods. The problem with closed domain methods is that you have to have an idea where your root is, all right? And that's not always possible. Again, imagine you're on an airplane, you only have pen and paper, and you develop a formula in your head and you want to solve for the root, but you cannot graph it. So you don't know where the root really is. Okay, so a more general approach would be to say, hey, I'm just going to pick a guess and let that guess converge to a solution, and let's see if it converges. Turns out there are methods like that. Most importantly, the Newton method, which is the one we're going to learn. I might skip the secant method because it's not really practical anymore. Although I said that in the learning objectives, we're going to learn about the secant method. I might just go and skip that and go directly to Newton's method, which is the most popular nonlinear solver method out there. Okay, so that's the overview. Now we can start digging into closed domain methods. They are very simple to comprehend and very intuitive, and we're going to develop a recipe for a closed domain method. We will start with what's called the bisection method. Okay, so with the bisection method, it's pretty easy. You say, I know there's a root somewhere. I'm going to pick 2 points, A and B, around that root. Okay, so they should be one root. One point would be to the left of the root. The other point is going to be to the right of the root, and we're going to refine that guess. And one method is to say, okay, take A and B and make a new guess for the root and take the point between those two and B. And now next, refine that interval. See where you are, if you are close to the residual function being 0 or not, and pick that new interval again, and then keep refining until you get to the root. Let's see how it works graphically. All right. So suppose that you are trying to find the root for this function. This is the residual function that we showed earlier, that was plotting earlier. And it's got a root somewhere over here, somewhere around 6.73, okay? And we know that that's the root, okay? And I'm gonna pick 2 points to bracket the root. I'm gonna choose A equal 3 and B equal 9, okay? You could choose A equal 6 if you want, and B equal 7, doesn't matter. just an illustration. Your method might, the initial guess might let you converge faster. Could be 1 or 2 iterations difference. That doesn't matter as long as you bracket the root. The next step is to say, okay, I've bracketed the root. How can I guess where the root is? We're just gonna take a blind guess and say the root is gonna be in between A and B. You could say it's gonna be 1/3 or 2/3 between A and B. It doesn't matter. We just chose to take it in half because that's kind of the simplest choice. Okay, so you find the midpoint, C. You call that C. You cannot see my hand. I'm pointing at C. You can see C over here. We're just gonna say C is our guess for the root, and it's going to be equal to A plus B over 2. So in this case, C is equal to 6. 9 plus 3 over 2, that's 12 over 2, that's 6. Okay. Now you check. You say, all right, I made a guess for the root. I took a stab at it. How do I guess if this is a root? We can simply just evaluate if this value of C makes the residual function equal to 0. We're never going to get exactly to 0, so we specify a tolerance. So we go and plug in that value and check if into the residual function and check if the residual function is less than a tolerance or not. If it is less than a certain tolerance, then great. Otherwise, we have to read. Now, the next step, you're going to be required to choose a new interval. So we started with A and B, and now we have C. Okay, this is the new guess for our guess for the root. Now, I'm going to use C to refine my interval. What is my new interval? Now, we said by definition, our intervals, our bracket needs to be to the left and right of the root. So clearly, I cannot choose A and C as my brackets because the root is outside this bracket. In this case, I need to make C and B as my new updated interval. And the way to figure this out, the way to know if the root is to your right or if your root is if you bracket a root or not, is to simply evaluate the function at all of those points and see the sign of the function. So remember that a function changes sign, okay, as it crosses the x-axis. Okay, so in this case, this function is negative to the left of the root, and it's positive, to the right of the root. So if I take the product of f of A by f of C, it's a negative value times a negative value, and it's going to be positive. So this tells me that A and C are to one side of the root, both of them. Okay, they're to the one side. If they were on the right side, again, the result will be positive. Okay, so if f of A times f of C is positive, then clearly A and C do not bracket the root. And therefore, C becomes my new point to the left of the root, and B remains as my old point. Now, you can choose to do this in many ways. I like to always say, take the product of f of A times f of C. If that product is negative, then A and C bracket the root because one of them is negative, one of them is positive. So then A and C is your new bracket. A is the lower bracket and C is the higher bracket. Otherwise, if f of A times f of C is positive, then C and B are your bracket. Okay, and then you choose C as the new lower bracket, and B would remain as your upper bracket. Okay, so in this case, we converted our C became our new A. So now we have a new value for the lower bracket, and the upper bracket remains to be the same. And then you repeat. Now we take the midpoint between A and B, and that midpoint is 7.5. And you can see we are starting to get close to the root. And then you keep repeating until you hit convergence, until f of C is less than a certain tolerance. And the algorithm is pretty simple. You start with the bracket A and B, which brackets the root of the residual function. You calculate a guess for the root, and that is A plus B over 2. Now, new values for your new interval. You're updating the interval, okay? And to do that, you got to make sure that the interval brackets the root. You take the product of f of A times f of C. This is how I like to do it. And if that's negative, then A and C bracket the root. In other words, A remains A, and C becomes your new value for B. Otherwise, it's C and B that bracket your root. C becomes your new value of A, and B remains the same. Check for convergence. Otherwise, if converged, just return the root, A plus B over 2. Otherwise, go back to step 1. Okay? And convergence is when you are close enough to 0. So if your residual function less than a tolerance, that's great. Or you can define a relative tolerance if you want, where you calculate the difference between iterations. We can talk about that later. But what's important here is just the algorithm. The easiest way is to just check if your guess for the root makes the function as close to 0 as possible. Okay, or your whatever tolerance you desire. All right. Now remember that f of a times f of c tells you whether a and c are the root or not. Similarly, f of c and f of b, you can do it whichever way you like. All right. So here's an activity for you. This is the algorithm. Now I want you to take the bisection algorithm and find the root of log of x equals 0. Now we know log of x equals 0. Log of x has a root at 1. In other words, log 1 is equal to 0. We know that the true value is 1. But I want you to do just 3 iterations of the bisection method by hand. Okay, do it, calculate it by hand. Take about 5 minutes to do that. Just implement the bisection algorithm. And I want you to start on the interval. Sorry, there's a mistake here. The interval should be 0.1 and 1.5. I have a little typo here. Let me correct that. Let me correct that. All right, I apologize about this. I fixed it. So I want you to find the root, use the section method to find the root of log of x equals 0, or the root of log of x, okay, with an initial bracket 0.1 to 1.5. We know that there's a root at 1, okay, so that's how I picked my bracket, right? Do 3 iterations of the bisection method and show me the value. Here's what you got to do. You pick A and B, you calculate C, you check for convergence, you pick new A and B, and then repeat, okay? Do 3 iterations, and I will see you on Zoom and we can discuss, okay? All right, I'm still showing the algorithm for you on YouTube. I hope it's visible, okay? Feel free to use your calculator, okay? And this is a natural logarithm. If you're done, let me know. We can start talking about the first iteration. Okay, Sammy is done. Okay, Matthew. Looks like Adriana's done all 3 iterations. Excellent. All right, I'll give you maybe 1 more minute. Let's see. I really wish you could turn on your camera so I can see you and get to know you. You don't have to, you're not required, but it does help me quite a bit. We're already all masked up when we're outside. No one sees anyone's facial expressions anymore. All right. Okay, let's see. Mitchell, do you want to guide us through the first iteration? Okay, Mitchell looks like he's not with us. Corwin.
Yeah.
Yeah, do you have an idea for what to do for the first iteration?
I think so.
Go ahead.
So I had A as 0.1 and then B is 1.5 and C is 0.1 plus 1.5 over 2, so that's 0.8. And then did the natural log of 0.8, which negative 2.23.
Okay.
And then to find like the next A and B values, I multiplied that by the natural log of 0.1.
Yeah.
That gave me a positive number, so I knew that I should use the C and B values for the new A and B values.
Excellent. Great job. All right. Second iteration. Let's see. Volunteers. Let's see. I seem like to pick the same people all the time. Yongshu, are you with us? Were you able to get the first iteration right? Okay. Let's see. Ellie, we've chosen Ellie before. Max? Okay. Gosh. Megan. Okay. All right. Looks like I'm having a hard time fighting people. I need a volunteer for the second iteration. Sammy?
I can go.
All right, James. Yeah. Go ahead, James. Sorry, Sammy, but you've had your fair share. Go ahead, James.
So did he say that his point was 0.8?
Yeah, his new guess for the root is 0.8. So you can start from there.
Okay, that became my new A, and then 1.5 was B.
Correct.
I added that together and divided by 2, and I got 1.15, I think.
Yeah, yeah. And then
the natural log of that was 0.13. And so I did A and B in between that because one's in between that.
Yeah. Well, you don't know that the root is 1. So in the code, you do not know what the root is, right? I gave you this problem because we kind of know where the root is just to set the stage. But in the code, if you know the root, you don't need to do any of this, right? So you need to check f of a times f of c. You need to know this to figure out where your root lies, whether to the left or to the right of your bracket. Okay. So when you chose your new c, which is when you got the new root, which is 1.15, right, and you chose that as your new b, you should have done f of a times f of c, and that should have given you a negative value. And then you'd say, okay, then my root is between A and C, so my C is the new B. Okay, so that's 1.15. All right, the third iteration is going to be the same thing. So I'll show you on YouTube how I did that. Okay. All right, we got a great team doing things. So let me show you how I would do this. You got it all right. I did the same exact thing. All right. So it does help sometimes when bisection with the bisection method with functions that are, with a single function to just plot it, kind of see where the root is. We know that this value is just around 1. Okay. And that's how I chose my A and B. A was 0.1 and B was 0.5. Okay. And then you make a guess. C is A plus B over 2. That's 0.8. So that puts C over here. Now, I'm showing the graph to help us visualize, but you don't rely on the graph to pick your new bracket because you want the code to keep running. You can't have the code do one iteration. This is one iteration, and then wait for you to say, oh, this is my new bit. You want the code internally to figure out what you are visually doing here. So when you visualize, when you look at this, you immediately know that there is between C and B, okay? But that brain is so sophisticated to see that. The code doesn't see any of that. To tell the code to see it, we have to multiply f of C by f of A. Now, for convergence, you get the log of this new root, and that gives you minus 0.223. That's not enough for a convergence criterion, I think. And then you have to check the new interval. So what I just said about the new interval, don't rely on whether you know the root or visually. You got to have the code do it automatically for you. Now, I'm visualizing this just to help you see what's happening. But when you take f of A by f of C, so this is A and this is C. F of A and f of C are both negative. So the product is positive. And therefore, we know that the function doesn't change sign, doesn't cross the x-axis between A and C. So we got to ditch one of those. We're going to keep B as our upper bracket, but our new lower bracket, we're not going to use A because we have a better guess than A. Now it's going to be C. So our new interval is going to be 0.8 and 1.5. And that's what happens here. 0.8 and 1.5 for our new interval A and B. Then you calculate C. It's A plus B over 2. Simply take the midpoint. Puts you at 1.15. Okay. Now you check for convergence. That brought our error from 0.2 to 0.1, which is great. We in half. That's great progress. Now we check. We know visually that the root is between A and C, but you gotta programmatically, you gotta take that product. So the product of f of A and f of C is negative because one of them is negative, the other one is positive. So that tells us that the function crosses the x-axis between A and C, and our A and C are therefore sufficient to define a new interval. A remains the same. C is going to be our updated B value or upper values. Think of A and B as lower and upper values of the bracket, right? So now we go again with 1.15 and rinse and repeat. Look at how we're getting close to the true root, which is 1, okay? And then you evaluate for convergence. We went from 0.1 to 0.02. That's about an order of magnitude, a factor of 10. See how we're homing in at the root very quickly. It's brilliant. Such a simple methodology. You just take a bracket, keep cutting it in half, called the bisection, because you're cutting it in half. Could you cut it by 1/3 or 2/3? Of course. Call that the trisection method, maybe, or the 2/3 homing in method. Doesn't matter, okay? But it's a rational mechanism to drive to the solution compared to just evaluating the function randomly in between A and B and trying to home in at the root, okay? And this is it. This is the bisection method. It's as simple as that, all right? Now we turn to Pythonify this, this algorithm. And I'm going to ask you a quick question now. And if you were to write the routine for the bisection method, I'm going to give you that routine, okay? But if you were to write it, what would you require for it to take as inputs, and what would you require it to produce as outputs, okay? Take a minute to think about that, and we can talk over Zoom about it, okay? All right, let's see. You're designing a routine called bisect, bisection, my bisection, the bisection method. Okay, what does it take as arguments? What do you need to give it to find the root, and what is it gonna return? Optional arguments, whatever you want, it's okay, just have at it. Abby?
Would we?
Oh, yeah, all right. I got many speakers. Go ahead, James.
Would we need to require the X values to be input, and then
X values, what
up,
X values?
like the A and the B or for whatever we're plugging into the function.
So be specific about the nomenclature. So you need the bracket, correct? I'm gonna write that down. That's correct. We need a bracket. What else?
I have a function as well.
Go ahead, Porter. Is that you?
Yeah, so I was working on this. I put a function in there as well, just like a generic function that then you can be able to evaluate at that point.
Yeah, so it would need, what is that function? What does that function correspond to?
The function we're trying to find the root of.
Yeah, that's specifically the residual function. Okay, we have to design. We have to be clear about. We're not solving f of x equal alpha. We're solving residual equals 0 always. That's, you got to be clear about your routine. So if someone comes in and says, "Oh, I want to find the root of log x equals 7," they cannot. What do they pass? Routine. They need to know that they need to pass log x minus 7. Okay, to find the root. So you got to be clear about that. And that's why we define the residual function to simplify the definition. All right, so we need a bracket, we need a residual function. Okay, what else?
A tolerance.
A tolerance, yes, thank you. Tolerant, tell it when we need to stop. What else?
A max iteration on this so it doesn't crash our computer.
Yep. Max iterations, good job. Now, you could pass this as an optional argument, tell the user to, provide it as an argument, or default it to a, certain fixed number of iterations, okay? But yeah, I like passing it as an argument, right? So anything else for the inputs? I personally don't think so. I think that's sufficient, okay? All right, what about the output? What does this routine return?
Should it return C, like a C
Yeah,
value?
the root. Yep, root. Perfect. At the minimum, it needs to return the root, right? Okay. Bailey,
maybe it returns an error.
Okay, Dylan,
like the error value.
Good. Yeah. It, I want to know. Okay, you found the root, but what error am I dealing with now? Clearly, that error is going to be less than the tolerance unless you bypassed your maximum number of iterations. So if you hit your tolerance, let's say you have a maximum number of iterations of 100. You do this over and over 100 times, and a tolerance of 10 to the minus 5. If you hit your tolerance at 15 iterations, great. Then you know that the error is going to be less than the tolerance. But it's good to return the error sometimes. What if you hit the 100 iterations and you never achieve the tolerance? I want to get an idea of what the error is. Am I at an error of 100 or 10 or 10 to the minus 4? Right, so it's good to return a tolerance. What else?
Well, technically, you could have it return the max iterations.
Or the actual number of iterations it took.
Oh, yeah.
Right? Yeah. Yep, good, yeah. You guys did. All right, I'll see you on YouTube. All right, great discussion we had on what we need to do to define our routine. I think you're all become good programmers. That's what I think about actually when I'm trying to implement a routine. I just put in placeholders and then figure out the rest as I move on. Okay. Keep messing up my focus on the slides. All right. So like we discussed, the routine needs at a minimum for inputs, you need the residual function. You need to be clear that you're passing a residual function, not just a function for which you find the root for. That root needs to be the intersection of a curve with the y-axis equals 0. You got to be very clear about this. You can't say, if you can't provide the option telling them, oh, you want to find cosine x equal log x, but they need to provide them the right-hand side. That's why we standardize with the residual function. We say, no, to solve that equation, you got to pass on cosine x minus log x, and then the routine will always find the root of that function equal 0. And that root is going to be the same as the original function. The initial bracket, a and b, a tolerance and a maximum number of iterations. And finally, for the return, you want to return at a minimum the root itself that you found, a plus b over 2, the error, which is optional. Hopefully, you hit the tolerance before you hit the maximum number of iterations, and the iteration count needed to find root. All of those would be helpful diagnostics. All right. So this is my implementation of the bisection method. I'm just giving it to you as is. We can dig into the meaning of the coding. I'll go through it real quick, but I'm going to leave that up to you. Unfortunately, we don't have much time in the course to go through each and every detail of this. That's why I've been giving you these codes. Feel free to dig into those and understand what I'm doing. But pretty quickly here's what I've done. I've provided I called the routine bisect. I provided the residual function f. I could have called it r, doesn't matter. A and B, the lower and upper roots, the tolerance, and the maximum number of iterations. Now I start by defining so clearly to check my convert. I could be doing like these the shadow things. I found myself trying to rotate my arm. Anyway, my hand. So I start by defining an error, and I need to start with a very high error, so that I know I'm not converged, so that I can at least start looping. And a number of iterations, I'm going to define that as a counter, started equal to 0. Now, I'm going to do this with a while loop, as long as my error is greater than the tolerance. In other words, once the error is less than or equal to the tolerance, this will stop. And my number of iterations is less than the maximum number of iterations, do the bisection method. First, I increment my iteration count by 1. I calculate the new root, and then I check if a times f of c is less than 0, then b equal to c, otherwise a equal to c. And then I calculate my error, which is the absolute value of f of c, and then the loop will just continue. Okay, it will auto check, then comes in, calculates the error, then it goes and checks. Oh, is the error greater than the tolerance? No. If not, continue. If yes, then return c, error, and the number of iterations. All right. Now, we're going to use also Python compare to our bisection method. Now, Python uses some advanced routines based on Newton's method, which we will learn at the end of the chapter. But for our intents and purposes now, we want to be able to use that function to compare our results to, right? So in Python, one way to do a nonlinear solve is through a function called fsolve. That's equivalent to the MATLAB fsolve, and it comes from scipy.optimize. So you just do from scipy.optimize import fsolve. And you just call fsolve, you give it the residual function and an initial guess, just one value, not a bracket, because this fsolve uses an open domain method, okay, which is great, simple interface. So we will just use that to compare to our function. And now comes actually getting our hands dirty with the parachute example. Go ahead and download the parachutist example with gaps Python notebook from Canvas. It's under the module Nonlinear Solvers, or you can find it under File, Jupyter Notebooks, Nonlinear Solvers. Go ahead and download that and go over it. There's multiple activities in it. The first one is on bisection, so just focus on that section, the bisection method, and go ahead and find an answer to our initial question, which is to find a drag coefficient. Okay, remember, you're designing a parachute to achieve a certain drag coefficient such that a 70-kilogram parachutist reaches a speed of 40 meters per second after 10 seconds of falling. Okay, that was the question. So go over the notebook and call the bisection method to find that answer for the drag coefficient, and then do it again for a velocity of 10 meters per second. Okay, so what if you want the parachutist to reach a speed of 10 meters per second after 10 seconds of falling? And we'll talk about the physics of that, but go ahead and download this and get started. I will see you on the other side. All right, my pupils, I am gonna go ahead and share my screen. So you just follow me on Zoom, and this will all be recorded on YouTube, or like my son calls it, YouTube. It's funny, every time he's like, can I watch Dino Train on YouTube, Papi? And so, all right. So I'm hoping you got that notebook. Go ahead and fire it up and follow with me on the screen. Can you all see okay on the share screen? So you're listening to me on, not on YouTube, you're listening to me on Zoom, okay? Okay, let's see, I'm gonna put you in, all right. So go ahead and let's get through the boilerplate. Import that first cell, and here's the description of the problem, blah, 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 etc. The equations, this is our residual function, and I have a typo over here, so this should be R, just call it R. I'm just gonna call it R. Okay, that's my residual function, okay? Now, specific, to be more rigorous, the residual function needs to be defined in terms of the unknown, the root you want to find. So in this case, we want to find C. So really, to be rigorous, this needs to be called R of C. Okay. So I go ahead here and define the residual function for you, and I define it as R of C, G equal 9.81. And it returns this thing, mg over c times 1 minus e to the minus c over mt minus u of t, okay? Excuse me. And I put in specific values over here, mg, m0 and t0, etc., because I don't want to pass those as arguments to the function. There's a reason behind that. It's because it complicates the implementation. So assume now that those m0 and u0 and t0, their values given to you, they are specified globally, and such that this function, just when it sees m0 anywhere in the code, is just going to use that value. And that's why I called it m0, u0, and t0 to specify, to indicate that those are user specified values. So, okay, so those are not arguments to the function. Okay, they are going to be fixed. Okay. So first thing I want to do is plot this residual function, and I create a linspace from 0.1 to 100. And here's what I defined: m0, the mass, 70 kilograms, t0, 10 seconds, and 40 meters per second. And when you run this cell, it's going to throw an error because we haven't defined the residual function. And here I'm plotting the residual function versus the drag coefficient, okay? Because we have fixed m and t and u. Okay, we fixed all of those variables, so that's a specific, we're solving for C, for a specific problem. So we want to look at how the residual function changes as a function of C. Is this clear? Yeah. Is this not clear? Let me ask the negative question. Does anyone find this confusing or not clear? Speak up. Okay. All right. So now you understand why I plotted it this way. If I were to change, let's take, a 50 kilogram parachutist, and I want them to hit after 20 seconds a velocity of 10 meters per second. If I plot this, it's going to change the curve. See, it changed it. So the residual function as a function of C is going to be different. Okay, it's going to have a different value for C once I change all of those other values, okay? So let's now just stick with 70, 10, and 40. We plotted it with respect to the drag coefficient, and we know that there's a root somewhere here, probably, I don't know, around 15 or something, okay? All right. So now we're going to choose our interval, as we know that there's a root between 10 and 20, so that's going to be our interval. Here's your bisection method. We discussed it in the slides. I just defined bisect, residual function, A, B, tolerance, maximum iterations, and it returns the root, the error, and the number of iterations, okay? Now, here's my question. Find the drag coefficient required for our parachutist, okay? So I redefine here U0 as 40 meters per second, but go ahead and call the residual function now. Call the bisection method on this residual function. Go ahead and fill the blanks. So what do you need here? We need a residual function, a bracket, okay? Let your bracket be 10 and 20, and a tolerance, I don't know, let's say 10 to the minus 5, and a maximum number of iterations, by 100. Put whatever you want. Okay, go ahead, run this and run it. Okay, and tell me what you get. The question is, what are you going to put in the first entry for the residual function? Any takers?
I think you're gonna put R.
R. Okay, that's the residual function, just the name of the function. And then we want our bracket to, let's say, 10 and 20. So what do we put?
10 and 20.
Yep, 10, 20. And B, for tolerance, let's do 1e to the minus 5. And for maximum iterations, I'm going to do 100. Go ahead and run this. All right. This is what I got. I got 15.21 for the, what is this? If you look at the function here, it's returning root, error, and number of iterations. So what this is telling me that my root is 15.21, that's the drag coefficient, with an error of 10 to the minus 6, and it took 20 iterations to get there, okay? All right, let's play around with this. Let's say I want a tolerance of 10 to the minus 8. It did it in 29 iterations. This thing converges nicely, all right? Let's say, 10 to the minus 10. It did it in 36 iterations. And the error is consistently less than my tolerance, okay? This is great. Now, can we do better? Let's say if I started with my roots with my initial bracket between 15 and 16. And I keep my tolerance 10 to the minus 10 and maximum iterations 100. Do you think it's going to take less iterations to converge this time? Yeah. Took 31 iterations. Not that much of a difference. But that's good because it's reassuring, because it tells you that no matter how, even if your bracket is huge, you're going to be off by a few iterations. Let's do a bracket between 1 and 50. 37 iterations. That's almost the same as doing the bracket between 10 and 20, okay? So, the choice of the bracket, as long as it's brackets the root, the number of iterations is not going to be significantly costly, okay? Such a big deal. All right. So now I'm going to change the question. I want you to find the drag coefficient for a velocity of 10 meters per second. Okay, so it's the same parachutist. M0 is still going to be 70. So M0 is 70 if you forgot that we defined now. My target velocity is 10 meters per second, and my time, I want to reach 10 meters per second after 10 seconds, okay? So 10 seconds, okay? I want to reach 10 meters per second after 10 seconds. What should my drag coefficient be? go ahead and punch in some numbers. Keep your tolerance at 10 minus 5 and put in put a number of iterations of 100. Just punch in a couple of numbers, okay? Let's stick with the 10, 20, maybe bracket, and let's see what happens. Any takers? Weston, do you have something?
Yeah, I punched the code in and it never converged.
Yeah.
So it says that, so it's giving me a root of 20, but my error is at 22. And then it went all the way to the number of iterations I allotted.
Yeah. So I suppose what you put is bisect R 10, 20, 1e to the minus 5, and 100. And this is what you got.
Correct.
Right?
Yes.
So clearly this didn't converge. And do you know why?
Is it because we have the wrong bracket in place?
Yes, we got the wrong bracket in place. All right. So let's to recognize this, to see this, let's just plot our residual function in terms of these values. So you see our root is over 60, somewhere around 68 or 70. Our bracket was 10, 20. So we were way off. Okay. So our bracket needs to bracket the root. Okay. So it should be between, somewhere between 60 and 80, the root. Okay. So now change the bracket, bisect R. Let's put, 60, 70. And again, 1e to the minus 5 for the residual and 100 iterations. And look at that. We get a root of 68.6.7 and an error 10 to the minus 7 with 16 iterations. Okay. So if you give it a bracket that brackets the root, you're good to go. It's going to converge. It is guaranteed to converge. There's no way for it not to converge, just by construction. You're always bracketing the root and you're going to home in on it. Okay. Now, physically, this makes sense. Think of it. In the first question, 70 kilogram parachutist, after 10 seconds of falling, to reach 40 meters per second, it gave us a certain drag coefficient. Now, if I want that same parachutist in the same length of time to reach 10 meters per second, what should happen to the drag coefficient? Should it go up or go down? It's going to go up because we need to put more drag to slow down the parachutist all the way to 10 meters per second. So the result makes sense. 68 is larger than 15 in this case, okay? Now, if you want to validate your result, go ahead and use the fsolve function from Scilab, and you get 68.666, 2 to 8, it's like almost to the same digits, okay? This is cool, huh? So now let's say you want to solve, and this is just an excursion. Let's say you want to find the root of log x equals 0, just like we were doing in class. Okay, what do? Bisect. Oops. Bisect. What are we going to give it? What's the residual function for log x equals 0? It's just log. Okay, p dot log. And then you give it bracket 0.1 and 1.5 and a tolerance of 1e to the minus 5 and 100 iterations. Okay, through an error and p dot log. It should be dot log. Sorry. Look at that. 0.999999999. Okay. But if you're finding the root of log x equal 10, you either define a new residual function, log x minus 10, okay, which is my preferred way. You say def my res function, takes it some variable x and returns np dot log of x minus 10. And then you go here and you say my res function. And look at that. Right? Okay. I am gonna stop the share and we can continue with our slides and talk about the regula-falsi method. Okay.
I have a quick question, Professor.
Oh yes, Abby.
On
Let me share the screen again.
Oh, it's not. It's just about the bisectional method in
Yes.
general.
Okay. Go ahead.
On like graphing calculators, they have that option where you can find a root by like picking something to the left of the root and then to the right of the root. Is this the sort of code that would be running in the background to solve for it?
I would not know. Is that a root finding approach in your calculator?
Yeah, like on just like a scientific one?
Yeah, it's probably just that. Yeah.
Okay.
It's probably just that. Yeah, because the calculator thing is going to have a hard time maybe implementing Newton's method. It's easier for it to do the bisection. It's a pretty simple method, right? You can do this while on an airplane, you know, and you guys going to be fed up. Like next time you're flying on an airplane, I feel like I've programmed you to grab an envelope and do a calculation with all the examples on the airplane. All right. I will see you on YouTube. Thank you. All right, now that we have nailed the programming, doing the bisection method, you can use it to your heart's content, and you can solve for nonlinear equations, etc. Have fun with it. And we are going to learn about another method, another closed domain method. The reason we learn about these methods is to just give you an intuitive feel of root finding and algorithmic thinking. All right. This next method is called the method false position, or the regula-falsi method. One might say, look, you know, you took a bracket and you divided it by 2. Why? Why did you choose to divide it by 2? Why not 1/3? Why not, you know, 2/3? Why not some other number? Okay, why not randomly pick numbers? So, you know, why shouldn't there be like a nicer way to do this? And one other way, taking up the ante, is to say, okay, rather than just halving the interval, let's draw a straight line between those 2 points, okay? Essentially trying to approximate the function. Let's draw a straight line between those 2 points and find the intersection of that line with the x-axis and call that our new root, and then repeat. So in other words, it's like approximating the function with a straight line, okay, between the bracket, and then finding where that line intersects the axis, which is the root, and then refining and refining. So that's called the method of false position, or regula-falsi method. All right, the procedure is simple. Since I've shown you how to do the bisection method, we're going to go through this with a little bit faster, but I'm going to ask you to do a couple of things. So we start with an interval, a and b. This is the same example of the function we started. In this case, a is 3 and b is 9. And again, you need to make sure that those a and b bracket the root. Both the bisection and the method of false position, or regula-falsi, your interval needs to always bracket the root. Then you draw a straight line between those 2 points, okay? In other words, like you're approximating the function by a straight line. And then what do? You intersect that line with the x-axis. That gives you a value for c, okay? So here's a rational, a slightly more convincing way of saying how you want to improve your guess of the root. Now that c, we claim, is going to be our improved guess for the root, and then we'll rinse and repeat. But now I'm going to ask you to do some algebra for me. So first, I want you to find a formula for this c. And once you find the formula for c, that's your regula-falsi method. Now, the line between a and b has a slope m equal f of b minus f of a over b minus a. So rise over run. That's the slope of this line. So now build a straight line with this slope and intersect that line with the x-axis and give me a formula for c. All right, go ahead and spend some time on this, and we can share our results on Zoom. just draw a straight line, call it y equal mx plus q, okay? And then you have m, find q, and then solve for the value of x that makes that straight line pass through 0. So in other words, where does that straight line equal to 0? What is the value of x for which mx plus q is equal to 0? And that is your value c, and that is your algorithm, okay? It's just some algebra. At the least, describe to me what you would do. So if your straight line is y equal mx plus q, what are the steps you would take to find where this line intersects the x-axis to find c? Just describe, at the least, just describe that procedure to me, okay? All right, any takers?
So this is just,
Okay, Sydney, go ahead.
so for finding Q, you would just, because we have M, evaluate it at either X equals B or X equals A.
Correct.
And so you could do F
Correct.
of A minus M times A.
Okay, so the first step is to find the intercept Q. So Veet, you had you were following up with us?
Yeah, it's the same thing, but I also had one question, like, can we find that from the midpoint thing or no? Because we have A, I mean, like A is 3, right? So there might be any intercepts, you know, so.
So Veet, this is what you're seeing on the slide is just a specific example. In general, C is not the midpoint, okay?
Okay, yeah, got it.
Yeah. So now Sydney told us how to find Q. So if the equation for our straight line is mx plus q, then we know m, we need to find q, that's the intercept, and you can get q just by evaluating that straight line either at A or B, it does not matter. Okay, I end up doing it at A or at B, I don't remember. It doesn't matter, the answer is gonna be the same. And then once you have the equation for the straight line, what do? How do you find C? Or the intersection of that straight line with y equals 0. Come on, when is ax plus b equals 0? It's when x equal minus b over a, right? That's it. So you have an equation of straight line. When it's equal to 0, that gives you the value of the root for that straight line, really, right? So that's what we're doing here. We're approximating the function by a straight line. We're finding the root for that straight line, and we're going to keep refining. Okay? I'll see you on YouTube, and then we can wrap up. All right, so here's how we do this. We know the slope of the line. And we're going to call that M. Now, I'm going to call the straight line formula mx, there's my hand over here, here's my hand, mx plus q. Okay, so we know M. Our goal is to find x that makes this line equal to 0, okay, this equation of the line. So we need to find q. Q, just like Sydney said, is simply the intercept and can be obtained by evaluating your straight line, y equal mx plus q, at any one of those, at any point, x equal a or x equal b. You know, if we choose b, for example, you would say just y at b equal m times b plus q is equal to f of b, which is a value that we know because we know b, right? And we know f, right? So that gives you q is f of b minus m times b. And then just if you just call that q, okay, just we know what q is, we know what m is. Now simply solve for the straight line equal to 0, and that is going to give you c. So at c, we know that the straight line is equal to 0. So y of c is equal mc plus q is equal to 0, and simply solve for c. That gives you c equal minus q over m. In other words, that's b minus f of b over m. And that is your bisection, that is your regula-falsi method, all right? And then you just keep repeating. Now we found c, you check, what is my bracket? F of a times f of c, is it positive? Then my bracket is gonna be to the right, so this is my new left point of the interval. This is my, that remains as my upper end of the interval. Then you draw another straight line, okay, between f of a and f of b, and then see where it intersects the x-axis, and rinse and repeat, right? Procedure is very simple to the bisection method, except the formula, rather than taking the midpoint, you're just evaluating the root of the straight line that connects f of a and f of b. And so you calculate the slope between f of a and f of b for the straight line, that's m. Then you calculate the point at which the line crosses the x-axis, that's b minus f of b over m. And then you check if you can check if you're converged, or you check kind of what the new bracket is, and then rinse and repeat, just like we did for the bisection method. And this is a definition of there's a little mistake here. Shouldn't be called secant. This should be called the regula-falsi method. I apologize for that. I'll update it next time we are working on this. We're not going to do this right now. We don't have much time in the lecture, but this is the algorithm. It's identical to the bisection method, except you are changing the way you're calculating your c, your root, your guess for the root. Here you see m, the definition of m, which is the slope, f of b minus f of a, etc. And then your c, your guess for the root, your error, everything else remains the same. Now this method converges a little bit faster than the bisection method. Both of those are closed domain methods, and we'll do the coding activity next time in class. And I will see you over Zoom where we will wrap up. All right. The hardest thing is when you still have one more activity to do and you run out of time. And I know you're all busy with many classes, so I'm not going to keep you any longer. But next time we follow up on this, we'll just go through the code, run again through the parachutist example, and do the regula-falsi method. I am going to go ahead and fix this typo over here. This should be regula-falsi, okay? So that it is always fixed. All right, so I'm gonna open the floor for any comments, concerns. Any comments, concerns?
A quick question about the bisection method or any of these methods. When you have like a parabola that only intersects at the top point, so it's going to be negative on both sides, do we just need to come up with a different way to decide which?
Yes. So those saddle points are problematic. Yeah, those saddle points are problematic. That's a very good point. Yeah, so those saddle points are problematic, and these methods that do not work for all methods. This is clearly the bracketing methods. They need to find, so with the parabola, you have a double root over there. That's part of the problem, really, because you have a double root over. This is a great question, Sami. In that case, a Newton method would be better as long as the initial guess is okay, right? Otherwise, you might be stuck because in many functions you might have low minima as well without a root, and you might be stuck, as we will see with Newton's method. But this one will not work. You have to have a change of sign for bracketing methods. Great question. It's a great exam question, actually. Actually, I think I had that in one of the exam questions. A good point, Sami. Any other comments before we do the life hack? Who was doing our life hack this week? This Thursday?
I don't think it was assigned.
It was not assigned? Oh. It was not. We were not assigned a life hack.
I guess you'll just have to share the one about the banana.
Oh yeah, I have to share the one about the banana. Thank you, Abby, for reminding. I was just kind of processing in my mind. I have one about how to tie your shoes, but it's gonna take a little bit of finagling. But the banana, I wish I had a banana. Let me see. Do I have a banana? I do not have a banana. Okay, so a banana has a stem on it, right? And in the other end where the flower, so there's the stem where it attaches to the, I don't know if you've seen a banana, a tree. It's like this kind of self-propagates. It keeps growing every year. The old one dies and then a new one emerges, and they're stuck, to their mother, and then there's the flower at the end. So every banana has a little stem, like a rigid stick, and the flower. How do you peel your banana? We have been taught to grab the banana and grab it by a little rigid stem, right? And you peel it, right? Okay, how often do you mess up your banana as you're trying to peel it from that rigid top? It becomes mushy, etc. Yeah, because that's the wrong way to peel a banana. To learn how to peel a banana, go ask a banana expert, the gorilla. Note how the gorilla peels the banana. They don't grab it from the flower side. They grab it from the rigid stem side, and they peel it from the flower side. And when you do that, you have a perfectly soft spot to grab the top of the banana, and you peel it, and you have actually the rigid stem acts like a cone, like a holder, like a banana holder, okay? And that's how I peel my bananas. I've never had any issues mushing my banana, trying to fight with it at the rigid stem. So next time you grab a banana, or right now after your lunch, try to peel it from the other side like a gorilla does. And that's my life hack. Anyone does it this way? Does anyone do it this way? You do. All right. Okay. Who told you about that? It just happened. But yeah, but it's surprising. We learn it the wrong way. I think it's the wrong way. Anyway, all right. Hopefully this helps. Okay. Thank you very much. See you soon. Bye.